Hello, and welcome to the next unit. This unit is all about parallel circuits. Parallel means that the resistors are going to be running side by each instead of one after another, as they did in a series circuit. It's important to understand the concepts of parallel circuits, as well as series circuits, because the majority of real-world circuitry is a combination of both parallel and series. So we have to understand the nature of both. The first thing we're going to do is we're going to look at the specific properties of parallel circuits. What is a parallel circuit? Then we'll looking at solving the different electrical values and how Ohm's law applies to a parallel circuit, and the four identities of current, voltage, resistance, and power as they pertain to parallel circuits, and any other tenets that may fall under parallel circuits. So let's get started. So far, we looked at the series circuit. And under series circuits, voltages add, current is common, resistance adds, and power adds. Next, we're going to look at the parallel circuit, which has a slightly different set of tenets. Once we have these down and we understand the differences between a series circuit and a parallel circuit, we can then apply those rules as they pertain to a combination circuit, where it would have both series and parallel components. But for now, let's focus in on the parallel circuit. So far, we've already gotten familiar with a basic circuit and the basic identities of a circuit, such as the potential difference in voltage between 2 points, such as our voltage source, E or V, measured in volts. We know that once a voltage is applied and a complete circuit is made to some sort of resistance or load, which is measured in ohms, then current will start to flow in the circuit. As the current flows in the circuit, the flow of the electrons through the resistance is going to start to generate some heat. We call this heat power, well, in this case true power, and we measure that in watts. The relationship of voltage is current times resistance. And to calculate power, we can use voltage times current. Here we have Ohm's laws, and we'll see how these apply to parallel circuits. So again, we apply voltage to a load, R1. Current will start to flow. But as we add a second resistance or a second resistor to R1, we see here that the tops of both R1 and R2 go to the negative side of the source, E. Both bottoms of R1 and R2 are connected to the positive side of the voltage source, E. So the voltage goes to the top of R1 without going through any other loads or resistances that will use up any voltage. And the top of E, the negative side of the voltage source, also goes to the top of R2 without going through any other resistances to eat up some of the voltage. And again, the bottoms of both R1 and 2 are tied to the return or the positive side of the voltage source E. So both R1 and R2 are getting the full voltage source, whatever that is. So V1 and V2 are the same as whatever the voltage is at the source, E. Same as before, when we connect these resistive loads to the source, current will start to flow. And the current will flow through both R1 and R2 at the same time. The total current, IT, has to be able to supply current to both R1 and R2. So the total current, IT, is the sum of I1, the current through resistor 1, and I2, the current through resistor 2. IT equals I1 plus I2. How much current flows in each resistor totally depends on the voltage as well as the individual resistances, according to Ohm's law. Since both resistors are tied back to the source, both R1 and R2 both get 120 volts in this example. Using Ohm's law, where I is equal to E over R, we can now use the subscript ET for all the voltages. It's not necessary to use V1 or V2 for resistor 1 or resistor 2 because it's not really a different voltage. It is the source voltage. So when resistors in parallel, we can just use ET. So you will see me use that as we move forward. Going back, I1 can be calculated from ET over R1, where the resistor will limit the current based on its resistance. R1 is 20 ohms, the voltage is 120 volts. That's going to limit the current in the first resistor to 6 amps. We call the different paths for the current branches. So resistor 1 is branch 1. And currently, in this particular example, branch 1 is going to conduct 6 amps of current. We can now calculate the current in branch 2. We're going to call that I2, or current 2, where current 2 is equal to the voltage source, ET, over the resistance of resistor 2, which is 120 volts divided by 30 ohms of resistance for R2, and that's going to limit the current to 4 amps in the second branch. So now we have 6 amps in the first branch, 4 amps in the second branch. That means the source itself has to be able to supply enough current to feed both 6 amps in branch 1 and 4 amps in branch 2. So IT equals I1 plus I2, or 6 amps plus 4 amps, which will give us a grand total of 10 amps that the voltage source has to give us. Now that we have the total current, we have the total voltage, total current, we can calculate the total resistance. Again, using Ohm's law, RT is equal to ET over IT, where we have a 120 volt source. It has to supply 10 amps of current. So the source thinks it's seeing or supplying only 12 ohms worth of resistance. You will notice that the total circuit resistance appears to be less than either R1 or R2. The total circuit resistance appears to be less than any individual branch. So what have we learned about parallel circuits so far? Well, we know that when we have two resistors that are wired in parallel, or as we say, side by each, where both the tops go back to the source and both the bottoms go back to the source, that each resistor will get the entire source voltage, where the voltage of R1 and the voltage of R2 will equal the source voltage, as well as any other parallel branches. We say that parallel branches have the same voltage. When we apply a voltage to a resistance, current starts to flow. And in a parallel circuit, each branch will draw the current determined by the resistance. The source current, or the total circuit current, IT, will equal the sum of the individual branch currents. Finally, the total resistance of the circuit will appear to be less than any individual branch resistance. Let's look at some more example problems and explore resistance in parallel to a deeper degree. Here we have a parallel circuit with 3 resistors, 16 ohms, 24, and 48 ohms respectively. They're connected to a 240 volt source. So, each resistor will get 240 volts worth of voltage across them. Now we can calculate the individual branch currents. Since we have total voltage and individual resistance, we can calculate individual currents, where I1 is equal to ET over R1, or 240 volts divided by 16 ohms. That will permit 15 amps worth of current in the first branch. Looking at the second branch, it's 240 volts over 24 ohms, or 10 amps of current will flow in the second branch. In the third branch, we have 240 volts, or the source voltage, over 48 ohms. This will permit 5 amps of current to flow in the third branch. The supply, 240 volts, has to be able to supply enough current to feed 15 amps in the first, 10 in the second, and 5 in the third. So IT is the sum of the individual branch currents. So when we add up 15, 10, and 5, the source has to be able to give us at least 30 amps worth of current. Since we have the total current and the total voltage, we can calculate what the voltage source is going to see as a total source load or resistance, where RT is equal to ET over IT, or 240 volts over 30 amps. So the source thinks it's supplying an 8 ohm load. And according to our observations earlier, the total resistance is less than any individual branch resistance. This is because, yes, we're adding resistors, but really what we're doing is we're adding more paths for current to flow. As we add more branches, we're adding more current. And that is the fundamental difference between a parallel circuit and a series circuit. As you add more parallel branches, you're adding more paths for current. As current goes up, it appears resistance is going down. There are many different ways to calculate resistance in a parallel circuit. I'm really only going to focus in on 2. So far, we've looked at this circuit as our last problem. And each branch drew a different current. The first branch drew 15 amps, the second 10, and the third 5, which gave us a total of 30 amps of current. We know that each branch is going to get the source voltage of 240 volts. So using ET and IT, we were able to calculate the total resistance. And we did. We calculated the resistance total as the total voltage over the total current, or 240 volts over 30 amps. And we ended up with a result of 8 ohms. But there's another way. that you can calculate total circuit resistance. There are others. This is only one example. We know that the total current is equal to the sum of the individual branch currents, where IT is equal to I1 plus I2 plus I3. If you look back at the example, we calculated each current, I1, I2, and I3, by using Ohm's law. Now, if we had RT, we could calculate IT by taking the total voltage and dividing by the total resistance, and we would end up back at our 240 volts divided by 8 ohms, or 30 amps. We did calculate I1 as ET over R1, which gave us 15 amps. We did calculate I2 as ET over R2, which gave us our 10 amps. And finally, in branch 3, we did calculate I3 as ET over R3. Using the application of substitution and algebra, we could substitute the value of IT for how we could calculate IT, where IT is really equal to ET over RT. And then we could substitute I1 for ET over R1. And also we could calculate or substitute I2 for ET over R2. And finally, I3 does equal or could be substituted for ET over R3. So now we have a new formula of ET over RT is equal to ET over R1 plus ET over R2 and ET over R3. Common to all of these fractions is ET. So if we were to simplify or factor out ET, inside we would have 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now, if I didn't care about the ET and I factored that out, or if you factor it out a different way, then the ETs will cancel themselves out, you'll simply end up with 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. This allows us to calculate the total resistance using only the ohmic values. Let's see how we can perform this mathematical operation using our example problem. Again, we had calculated the current in branch 1 to be 15, the current in branch 2 to be 10 amps, and the current in branch 3 to be 5 amps. We added those together to give us a total of 30 amps. We then used ET over IT to get RT, which gave us 8 ohms. So we know that is the answer that we must get back to. So if we take our new formula, which is the reciprocal of the reciprocal sum, will give us the total resistance. So if we take 1 over RT is equal to 1 over 16 ohms plus 1 over 24 ohms plus 1 over 48 ohms, or a 16th plus a 24th plus a 48th. When you go through that addition of the fractions, you find out that 1 over RT is equal to 1/8. In order to get back to RT, we have to take the reciprocal of each. So we have to take the reciprocal of 1 over RT, which gives us RT, and the reciprocal of 1/8 is 8. So sure enough, we get back to our answer of RT is equal to 8 ohms. Here's a new problem. Again, I have 3 resistors in parallel, and I have a source voltage of 600 volts, which is a standard Canadian 3-phase voltage. I'll give you a couple of minutes to sort out the solution. I would like you to find each of the individual branch currents, the total current, and then using ET/IT/RT, calculate the total resistance. And then practice using the 1/RT formula to calculate the total resistance. I'll give you a couple minutes to figure that out. Do you have a chance to figure it out yet? Let's take a look. The first branch circuit is 600 volts divided by 30 ohms, or 20 amps. The second branch circuit is 600 volts over 40 ohms, or 15 amps. The third branch circuit is 600 volts over 120, or 5 amps. And once we have the 3 individual branch currents, we can add them all up and get our total current of 40 amps. Now that we have IT, we can use basic Ohm's law of ET over IT will give us our total resistance. And if we divide 600 by 40 amps, we'll end up at 15 ohms. Knowing that the total resistance must be less than any individual branch resistance, this seems plausible because 15 ohms is less than any of the individual branches, 30, 40, and 120. Now let's use our reciprocal formula, where 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Or 1 over 30 ohms plus 1 over 40 plus 1 over 120. And when we take the final fraction and flip it, sure enough, we get a total resistance, RT, of 15 ohms. Here's another practice problem. Here we have 3 resistors, 6 ohms, 15 ohms, and 10 ohms, all in parallel. And we've attached them to a 30-volt source. So for this problem, I'd like you to calculate all the individual branch currents, the total circuit current, the total circuit resistance, and you can use either or both of Ohm's law, ET over IT, or use the new reciprocal sum formula. And in addition to that, I would like you to calculate all the powers. The powers in resistor 1, the power in resistor 2, and the power in resistor 3, and the total circuit power. So I'll give you 2 minutes to try that, and then we'll look at it together. Hopefully you've had enough time to complete this problem. So, using basic Ohm's law, we can calculate each of the branch circuits, currents. So in the first branch, you'll have 5 amps. In the second branch, 2 amps. In the third branch, we'll have 3 amps. The total circuit current is the sum of the individual branch currents. So if we add those up, we end up with 10 amps. Now that we have the total circuit current, we can find the total circuit resistance again using basic Ohm's law. And we end up with 3 ohms. We also could have exercised the reciprocal sum formula and again arrived at 3 ohms. All our power formulas still hold true, as long as we only use values from our individual specific areas. Such as if I'm calculating the power for resistor 1 or power 1, I have to use the voltage at 1 times the current at 1. And so on and so forth, where P2 is EI2 and P3 is EI3, which will respectively result in 150 watts, 60 watts, and 90 watts. If we add the powers up, the sum of the powers, we end up with 300 watts. How do we know that we can just add the sum of the individual wattages and get the total circuit power? Well, if we go back to our original Ohm's law formulas and we do PT is equal to ETIT, or 30 volts times 10 amps, we again arrive at 300 watts. So now we've looked at the basic tenets for parallel circuits. Voltage is common, currents add, resistance adds inversely, or a reciprocal sum, and powers add. Let's examine currents just a little bit more. Here I have 3 ammeters. The first ammeter has 5 amps. The second one, if you wish, has 2. And the third has 3. Now the current is going to be coming along in the 5 amps, and that's going to reach a junction. And we call junctions, where resistors will branch off current, we call those a node. So any point where a branch circuit peels off current, we call that a node. The physicist Kirchhoff stated that the sum of currents entering a node must equal the sum of the currents leaving. So in this example, we have 5 amps coming into the node. 3 amps are leaving the node. Since 5 are coming in and 3 are leaving, 2 amps must also be leaving. So 5 amps is coming in and 5 amps must be leaving. We call this Kirchhoff's current law. We also sometimes refer to it as nodal analysis, where we can examine the currents coming into a node and figure out what the currents are that must be leaving the node. Again, we refer to that as nodal analysis. So let's look at Kirchhoff's current law, or nodal analysis, as it relates to the last problem we did together. In the last problem, we calculated out the 3 currents to be 5 amps, 2 amps, and 3 amps, and that the circuit total current must be 10 amps. Here are the 4 nodes associated with this circuit. Again, a node is just any junction where current can come or go or enter or leave. So we have a total of 10 amps, and it's going to come into the very first node. According to Ohm's law, we calculated that that first branch will require 5 amps. So 10 amps will come into the node, 5 amps will leave and go through R1, which will leave a remainder of 5 amps to keep moving along to the rest of the circuit. That 5 amps will then come to the next node. 5 amps enters that node, but 2 amps go to feed branch 2, which leaves a remainder of 3 amps to carry on to feed R3, or the third branch. The 3 amps at the end will move along and then enter the next node. So now I have 3 amps entering the node on the bottom. It will meet up with the 2 amps from the second branch. So now I have 2 amps entering and 3 amps entering, which means I must have 5 amps leaving. This 5 amps will come along to the next node. It will meet up with the 5 amps from branch 1. And I will end up with my resultant of 10 amps for my total circuit current. Whatever the current is that's entering the circuit must also be the current that is leaving the circuit. The circuit must be balanced, and it will be, it should be, it must be. This is the basics of nodal analysis, and using Kirchhoff's current law to figure out what current will be flowing in which conductor. Let's do one more practice problem. Here we've got 3 resistors in parallel hooked up to a 240 volt source. 60 ohms, 120 ohms, and 40 ohms. Go ahead and work out all the individual currents, the total circuit resistance, all the individual powers, and the total circuit power. I'll give you a couple minutes to do that. So let's take a look. The first current should be 4 amps. You should have gotten 2 amps for the second and 6 amps for the third. The total current being the sum of the individual currents, when you add those up, you should have arrived at 12 amps. Once you have the IT, you can easily find RT, and you should have arrived at 20 ohms. Or you could have done the reciprocal sum and ended up again at 20 ohms. The individual powers should calculate out respectively to be 960 watts for the first, 480 for the second, 1440 for the third. Adding the powers up should have given you 2880. You could have also calculated the total circuit power by ETIT, and again arrived at 2880. It's a good practice to try a couple of different methods to see if you can arrive back at the same result. If you do, you can pretty much go with confidence that you've answered the question correctly. Let's look at one more before we wrap up. Here I've got another problem. This one's a little bit different. It's different for a couple of reasons. One, it's got 4 resistors in parallel. 20 ohms, 40 ohms, 60 ohms, and 120. I've got all the resistances in each of the branches, but I'm also supplying you with the total circuit current of 12 amps. So for this problem, I want you to find all the individual branch currents, as well as the circuit voltage, probably the total circuit resistance, each of the powers, as well as the total circuit power. So all values, all currents, all powers. I'll give you a couple of minutes to work on that. So you've got total current. In order to get total voltage, because you need the voltage to calculate each branch current. You could do what they call a current divider and do ratios. But it might be easier just to find the total circuit voltage. To find total voltage, I would need total resistance, which means that I would have to use a reciprocal formula. And when you do that, you come up with 10 ohms. Now it's a simple Ohm's law problem. ET is equal to ITRT. Total current times total resistance will give me total voltage. 12 times 10 is going to give me 120 volts, which means each branch is going to have 120 volts applied to it. Now I can find the current in branch 1, which is 6 amps. Branch 2 is going to receive 3 amps. Branch 4 is going to get 2 amps, and the fourth branch, the last branch, is going to get 1 amp. If I add up the 6, the 3, the 2, and the 1, then again I get back to my 12 amps. Now that I have a current, a resistance, and a voltage for each branch, each location, I can calculate out the powers. Probably the simplest way is just good old PEI, which would give me 720, 360, 240, and 120 watts, respectively. If I take the sum of the individual powers, I end up with 1440 watts. To check my answer, I'm going to do PT is equal to ETIT, or PEI, which again will get me to my 1440 watts. Again, it's always a good practice to double check your answers. So in summary, what do we know about parallel circuits? What are the concepts that reside around parallel circuits? Well, voltages are common across all parallel branches. The total circuit current is the sum of the individual branch currents. From that, we looked at Kirchhoff's current law, which states that the sum of currents entering a node must equal the currents leaving the node. We call this nodal analysis. Total resistance of the circuit must always be less than any one branch resistance in a purely parallel circuit. And that only applies to a purely parallel circuit, or parallel branches. We can calculate the equivalent resistance of parallel branches by using the reciprocal sum. Finally, it doesn't matter whether the circuit is series, parallel, or even a combination for that matter. Powers always add. This concludes the presentation for parallel circuits.